Welcome to part 3 in the series An Introduction to the Derivative. In this example, we want to find the derivative of y with respect to t of the function 2 over t. So we're going to use a slight variation in our limit definition, and in this case it's going to be delta t approaching 0 because our variable of differentiation is t, and that's f of t plus delta t minus f of t over delta t. So we have 2 over t plus delta t minus 2 over t all over delta t. Now in this case we can't evaluate this limit through direct substitution because of this delta t down here, so we're going to have to do some manipulations. So let's get a common denominator. So this times this is 2t. This times this, using that sign, is minus 2t minus 2 delta t all over this times this, which is t times t plus delta t, and the whole thing is over delta t. Now, this term, this delta t down here, this is delta t over 1. So I can change this division to multiplication by taking the reciprocal of my denominator. So this whole thing is equivalent to t 2t minus 2t minus 2 delta t all over t times t plus delta t times 1 over delta t. Which brings the delta t in line with this term here. So we can see here that the 2t and the negative 2t cancel out, and we have a delta t divided by a delta t here. So this, well, let's rewrite first so we don't get confused. So we have a negative 2 delta t in the numerator, and we have delta t times t plus delta t times t. These delta t's will cancel out, and what we have at the end is negative 2 over t times t plus delta t. Now this is what we'll take our limit of. So let's bring our limit down to here, and we take our limit as delta t approaches 0 of negative 2 over t times t plus delta t. As we do this, this goes to 0, and our final result then is negative 2 over t times t is t squared. Now, as we can see in this example, just as in the last example, that the derivative function isn't defined at the point t equals 0. And so we come to the point in our discussions of differentiation where it's time to look at what does it mean for a function to be differentiable. And we're going to connect that discussion with an idea of continuity, or whether the function is continuous. So first we need to look at when functions are differentiable and where functions are differentiable. Let's revisit our slope of our secant line from a slightly different perspective. Let's take a look at it from the perspective that we want to find the slope of the tangent line at some specific constant value c. So we can see that as this x value approaches c, the slope of the secant line is going to approach the slope of the tangent line. So that gives us a slightly different form of our limit definition of derivative. So what we're going to have is the limit as x approaches c of f of x minus f of c. So this f of x value minus the f of c value gives us this difference in here. That's the difference of the y's, divided by the difference of the x's is simply x minus c. This is the alternative form of derivative, and it's an important form for a couple of reasons. It's used in some proofs, but it's also used to determine derivatives in a slightly simpler fashion. We're going to use it in our discussion on differentiability at this point. We're going to investigate differentiability in 3 different instances. And the first situation we're going to look at is a discontinuous function. For this situation, we're going to employ the greatest integer function. And as you can see, the greatest integer function is discontinuous at any even integer value. And so what we're going to do is we're going to apply the alternative form of the derivative to this function, and we're going to apply the limit from the left and from the right and determine what happens as we do that. So to rewrite the limit, it's the limit as x approaches c of f of x minus f of c over x minus c. So we're going to take this limit from the left first. So the limit as x approaches 0 from the left of f of x minus f of 0 over x minus 0, which is okay. So f of 0, this function evaluated at 0, is just 0. So this expression is actually the limit of this. So as this value approaches 0 from the left, this is an increasingly small negative number. This value is going to be -1 as we get closer and closer. So negative over a negative is a positive number, but this number is getting closer and closer to 0, so this fraction is getting bigger and bigger which is going to positive infinity. So we can see that the limit from the left is infinite, which means this limit doesn't exist. So now we're going to do the same thing, and we're going to take the limit from the right. And we're going to do the same exact thing. F of x minus f of 0 over x minus 0. And here, just as we did before, this value is 0, so we have the greatest integer of x over x, and we take that limit as x approaches 0 from the right. So as x approaches 0 from the right, the function is always going to be 0 as it moves down. So this is going to be 0 over some number that is also approaching 0. So 0 over anything is simply 0. And now we have a condition here where the left-handed limit and the right-handed limit are different values. And from our discussion on limits, when the left-handed limit differs from the right-handed limit, the limit of the function doesn't exist. So this function is non-differentiable because it is discontinuous, because the limit from the left and the limit from the right are differing values, therefore the limit doesn't exist. So the greatest integer function is non-differentiable at any even integer because it is discontinuous. In general, any function that is discontinuous is non-differentiable at the point of discontinuity. This greatest integer function is differentiable someplace in between each integer value, but it is non-differentiable at the ends because of what we just discussed. Now let's take a look at a second situation where a function is non-differentiable.